Logarithmic differentiation worksheet solutions. I'll just do the first page in this one. In this first problem, you're asked to kind of prove two derivatives. Show that the derivative of the natural log of x is 1 over x, and the derivative of log base b of x, so any log, is 1 over x times the natural log of b. And the way you do that, you can use implicit differentiation. What I mean by that is set these up as equations, so maybe y equals the natural log of x, and then try your best to find y prime. And well, you can't just take the derivative of both sides right now because we don't know the derivative of natural log of x. That's what we're trying to show. But I could do e to both sides of the equation. And that would give me that e to the y power is equal to e to the natural log of x, which is just x. And now I can take the derivative of both sides of the equation. That gives me e to the y times y prime equals 1. So y prime is equal to 1 over e to the y power. But since y is equal to the natural log of x, this is 1 over e to the natural log of x power. But 1 over, or e to the natural log of x is just x. So what I get is that y prime is 1 over x, which is what I was trying to show right here. Similarly, it's really the exact same argument if you have y equals log base b of x. The only difference is instead of making it e to the y equals x, I'd have to make it b to the y equals x before I take the derivative of both sides. The derivative of b to the y is b to the y times the natural log of b times y prime. There's a chain rule going on there. And the derivative of x is just 1. So from there I can solve for y prime by dividing both sides of the equation by b to the y power times the natural log of b. Get this y prime all by itself. But then I'll do the same trick that I did on the other side. Y is equal to the log base b of x, so I have b raised up to the log base b of x power times the natural log of b. And b raised up to the log base b of x power is just equal to x. So I get 1 over x times the natural log of b, which is what I was trying to prove. Okay, that's all just proving these two facts. The rest of these problems will kind of use those facts. So this problem just asks you to find the derivative of the natural log of 1 over x. Two options. Option 1 would just be to use the chain rule. So I got the derivative of the natural log of something. Well, if it was natural log of x, it would be 1 over x. But it's not. Playing the role of the x is this 1 over x. So I'm not done. I then have to multiply by the derivative of 1 over x. So I get 1 divided by 1 over x times the derivative of 1 over x. Well, 1 over x is x to the negative 1 power. So I can bring the negative 1 down in front and subtract 1 from the exponent to get x to the negative 2 power. But 1 divided by 1 over x is just x. So really what I have here is x times negative x to the negative 2 power. And that's equal to negative x to the negative 1 power. In other words, negative 1 over x. So here's one way you could do this problem. Another way you could do this problem is you could say that this is equal to the derivative of the natural log of 1 minus the natural log of x. Haven't done any calculus here. I just noticed that the log of something divided by something is the log of the top minus the log of the bottom. That's this second log rule right here. Natural log of 1, turns out that's 0. You don't even need to know that that's 0 because that's just a constant. So it's the derivative of this constant, the natural log of 1, minus the derivative of the natural log of x. So it's 0 minus the derivative of natural log of x is 1 over x. So I end up with the exact same answer that I had over there, that it's equal to negative 1 over x. All right, what about 1 over the natural log of x? A few ways you can do this. I think I prefer to do this using the chain rule. So this is the derivative of the natural log of x raised up to the negative 1 power instead of 1 over. So first I'll take care of this negative 1 using the power rule. So I got negative 1 natural log of x to the negative 2 power. But then I'm not done. I have to multiply by the derivative of natural log of x, which is 1 over x. So I get this mess right here, which if you want to clean it up a little bit, you could say it's negative 1 divided by x times the natural log of x squared. If you felt like it, this cleans up to this. All right, getting a little bit nastier looking down here. what I'm going to do to make this problem a little bit more palatable is rather than just power through with the chain rule, I'm going to apply a whole lot of log rules first. Because I think if you just use the chain rule and the quotient rule, it's just going to be a mess. So using my first log rule, I can say that this is the derivative of, how about this? Using a bunch of log rules, you can get that this is 1/3 times x to the 5th power plus, 1/3 times the natural log of x to the 5th power plus 3x squared minus 2 times the natural log, how about 2 parentheses, natural log of x plus natural log of e to the x. So all of this was just applying log rules, something divided by something. The log of a quotient is equal to the difference in those two logs, so I could split it up in those two logs. And then I could take exponents like this 1/3 right here and bring it down in front, and exponents like this 2 and bring it down in front. And then I have a product of things x times e to the x, so I can break that up into two different logs here. And before I take the derivative of this, I'm going to do one more step of simplification. I'm going to leave this side alone. And maybe that bears repeating. You can't break this up into two different logs. We don't have a log rule for the natural log of a sum. But over here, I can say this is minus 2 natural log of x, and then the natural log of e to the x is just x, so it's minus 2x. So really what I'm being asked to take the derivative of is this thing right here, which will be a lot easier to take the derivative of than just going through with the chain rule on this guy here. So I can do that. Let's say I'll leave the 1/3 alone. The derivative of natural log of x is 1 over x. Playing the role of x is x to the 5th plus 3x squared. But then I still have to take the derivative of that x to the 5th times 3x squared. This is chain rule here. So that's 5x to the 4th plus 6x. And then from that I want to subtract 2 times the natural log of x. The 2 is just a constant, pull that out in front. Derivative of natural log of x is 1 over x. Minus 2 is a constant, derivative of x is just 1. So I get that that's equal to this thing, which I can clean up a little bit. I don't care a whole lot about simplification, but when it's easy enough to do it, I tend to do it. 5x to the 4th plus 6x divided by 3 times x to the 5th plus 3x squared. If you felt like it, you could factor out an x from this and cancel it with an x from that. I don't feel like it. Minus 2 over x, minus 2. Fine. If you felt like getting a common denominator, you could do that too. I don't feel like it. So I'm going to call this my final answer here. All right, moving on. This mess, again, much like the problem up here, you could just power through and use chain rules and quotient rules, but I'm not going to. I'm going to use log rules. So I'm going to say that this is the derivative of the log base 2 of 4 raised up to the 2x plus 1 power minus the log base 2 of 2 raised up to the x e to the x power. And the reason I'm going to do that is that it'll allow me to use a whole bunch of log rules. I can take this 2x plus 1 and bring it down in front. So I'm still not doing any calculus here. 2x plus 1. The log base 2 of 4 is just 2. Because that's asking, do I have to do that in another step? No, I'm going to talk about it. That's asking me what power does 2 need to be raised to make it a 4? And that answer is just 2 right here. Minus, I can bring that x e to the x down in front. And then I got the log base 2 of 2, which is just 1. So really this question is asking me what's the derivative of 2x plus 1 times 2 minus x e to the x. And I can figure out that derivative. This 2 is just a constant, so it stays out in front. The derivative of 2x plus 1 is just 2. So 2 times 2 is 4. Minus the derivative of x e to the x, I'd have to use the product rule. The derivative of x is 1. E to the x plus, leave the x alone. The derivative of e to the x is e to the x. So I'd end up with something like that. Last one on this page, find the derivative of x times sine of x without using the product or the quotient rules. Without using the product or quotient rules. I guess that's proper English. That might seem impossible. It's something times something. How the hell am I going to do that? Well, the trick will be to set this up as implicit differentiation. So y equals x sine of x. And then I'll try to find y prime. But again, you can't really find y prime unless you take the derivative of something times something. Or maybe you divide both sides by x, but then it's something divided by something. Either way, it's the product or the quotient rule. Unless you get clever and you take the natural log of both sides. Really, you could take any log of both sides, but I prefer the natural log. And the reason you do that is because the natural log of something times something is the natural log of the first thing plus the natural log of the second thing. So what I now can do is take the derivative of both sides of the equation without using the product or the quotient rule. The derivative natural log of y is 1 over y times y prime. The derivative natural log of x is 1 over x. And the derivative of the natural log of sine of x would be 1 over sine of x times the derivative of sine of x, which is cosine of x. So what I get is that y prime is equal to y times 1 over x plus cosine of x over sine of x. But I don't want to leave a y in my answer because y is this x sine of x thing. So my final answer, or one version of my final answer, might end up looking, I don't know, something like this. Yeah, I'll show off cosine over sine. I know that's cotangent, so I'll write that like that. But here's y prime, and I didn't use the product or the quotient rules. This trick that I just used is called implicit differentiation, and that's what we're going to be doing on, it's called logarithmic differentiation. And it's what I'll be doing on the second page of this worksheet, which I will do in the next video.